So also very warm welcome to this closing session of this really nice Torsional Vibration Symposium. I'm really honored to give a talk on a topic where I'm really enthusiastic on, and I really put a lot of work into this the last couple of years. If we look in the exhibition booths outside, digitalization plays an important role. Everybody's talking about it. Everybody is using words like big data, artificial intelligence, IoT, and it's really somehow difficult to catch what is behind it. What does it mean for our daily business? And this was exactly the motivation where I was writing a paper on this topic, to not only see what the fancy outcome of this whole process looks like. I want to really shed light on the process, how to work with such amounts of data, how these new technologies can help us. They do not should us hinder about our standard work. They should really help us. And this is what I will understand under the title New Opportunities for Big Data Analytics. So first of all, I want to give a motivation why to use big data in torsional vibration analysis. Some of you might ask, well, we have already our tools, we have already our measurement principles. Why to go the extra mile? To do something really workful with a lot of work behind. Because it's a lot of work behind, it's also a new technology that is incorporated into your daily business, which also is outlined to some challenges and to restriction and limitation in your daily business, which you have to somehow solve before you start your business on these topics. And afterwards, I show you some case studies. 2 case studies which might, from a purely technical point of view, from a data analyst, from a data scientist, might not be the most sophisticated one. But these 2 examples I want to show you are somehow showing what the process of big data analytics is capable of and how to use it in our daily business. Let's come together and make a brainstorming round and think about any marine application. What are the impacts of torsional vibrations? What parameters do we have to know to really capture the entire problem? And if you sit down, there are dozens of parameters. Torsional vibration is such a diverse topic. You can even fill a 2-day symposium every 3 years with a lot of high-level contributions to it. And it's not getting easier in future, I can promise you. But also on the other hand side, to really capture all the details, there's a demand of a lot of context information. If you're doing analysis or monitoring of your components, you need to get a picture which is just above the components that you are monitoring. And as I have said, future is not going to be much easier. If you think about emission regulations, we have talked a lot about emissions. And what we know is there's a drive in the industry if emission regulations tends to be more and more strict. For instance, we're discussing heavily on how the impacts of different fuels are. What about multi-fuel concepts? What about hybridization? We have seen today the increased complexity of systems for the analysis when we talk about hybridization, multi-fuel concepts. And also something which is from an operational point of view rather interesting is we are also at the status where also the operation of our vessels, of the powertrains, might be different. So we are tending towards something like an autonomous operation in shipping. How it looks like, we don't know at the moment. We are tending to provide predictive maintenance concepts to components. And to do this, everything, we need some kind of additional features, additional simulations or data strategies. However, all turns around the question, how does the powertrain of the future looks like? And as digitalization is somehow always in this topic involved, I see it also the possibility to be a driver of the whole process, to really start going on and start tackling new things. I've here written some buzzwords which might come from any marketing team, like big data, artificial intelligence, IoT. And it's all something that really is not really touchable for the daily analysis in our life. what does it mean for? And for this reason, I want to also give my motivation why I'm thrilled to really improve those knowledge in this perspective. If we do not know what the powertrain of the future looks like, we also do not know what the torsion vibration of the future might look like. And there are two questions. Today's powertrains that are delivered, how many times will they be retrofitted? How many times they will change their dynamics? And also, if we think about long-term involvement, and long-term involvement 10, 15, 20, 30 years in future, I'm really curious about what kind of torsion vibration I'm dealing with. And for this reason, we have decided to go the extra mile and to do a data-driven development of our analysis products. However, inserting your big data infrastructure into your daily business is rather difficult. First of all, setting up the big data infrastructure, so just getting all the data around is already hard work, but it's by far not the end of the story. Setting up the infrastructure is not sufficient. You have to really do the analysis with it. You have to somehow get some information out of the data. And without analysis, no knowledge will be gained immediately. Which of course comes to another topic. Who should do this work? You have to be sure that everybody is very busy, a lot of emails coming today. And then we should work with gigabytes of data day by day. Probably they are telling us the same as the day before. What should it be done? Should we really scale up our experts? And even if we would that, it's not possible to find experts on vibration analysis, maybe except for this round today here. And the last thing is, we have seen that there's a rather diverse topic, and there's a lot of context information coming from a lot of different parties in the system. And we need context information. We have seen it in the last two talks that teaming up or sharing data is something very different. And it will definitely generate a win-win situation. However, as long as all involved parties are willing to do the extra work on it. So what should we avoid is the following. The data monster. Come and break and limit all your expert resources without really gaining anything in the daily business. And I want to give some insights into how such big data amounts can be used in daily business. To start with, I want to provide two different approaches how to work with big data. One is a rather classical one, the physics-driven approach, understanding what has happened, and the other thing is collecting a lot of data and work with the data. The physics-driven approach is all about an analytical representation of the quantity that we're monitoring or measuring. It's all about simulation, all about understanding what the context information is doing with. And it's clear that you know that you need to know anything about the domain where you're working is, because adding, for instance, an additional parameter to a simulation might be a rather tricky thing to do, and you need to do a lot of work to do this. So this is the side always connected to the question, what happened? Something new from my perspective, so at least I figured out the last couple of years, is the purely data-driven approach. So it's the statistical representation of the quantity of interest. It's all about predicting, finding correlations between data. It's all about identifying trends. And what first and was not really clear to me is domain and expert knowledge in the physical domain is at first sight actually not necessary, and you can input any data you want to do. The question is, did something happen in the data? So, and here, at this point, it is clear that the pure data-driven approach cannot tackle the entire problem. And the physics-driven approach, either not, because it's the time-consuming part. So we have to somehow find ways how to effectively combine those two. And for this, I want to show you first one, starting from the physics-driven approach, and afterwards for the data-driven approach. So we have now here a 7-cylinder, 2-stroke main engine propulsion system It's a car carrier vessel with a controllable pitch propeller. We have here just a separate data set from an entire week where we can see the port-to-port navigation of the system. And we have in the middle picture here the vibratory angle at the free end of the crankshaft over the entire week. And what we can see is we have essentially two speed levels we are working with. We have extremely small amplitudes. We're around 1 milliradians. And between the two speed levels, the red and the gray one, we have huge deviations between. So if you give this task to any torsional vibration analyst, one would say, well, during this week there were a lot of different loading conditions, operation conditions, different weather and wave conditions. What can I say? Without context information, not much. I know if you can give me a limit and all the values are below, I can say everything fine. But if there's not a limit, how to judge this? And here comes the information. What do we need for an analysis? And to start with the controllable pitch propeller, the pitch of the propeller is a natural source of data input. And what we can see immediately is how the two data clusters are spreading up to really find a smooth curve or identified correlation between the vibratory angle at the free end and the propeller pitch, which is nothing really surprisingly. However, it's nice to see it at this picture. Of course, propeller pitch is always connected to shaft power transmitted, and we can even see a better picture. So we have now rather intuitive parameters used. Let's go one step further. What about the navigational speed? And even in navigational speed, we can see much more information than for the standard revolution per minute from the main engine. And to go even one further step with a parameter that is not commonly used for TVA, at least we don't use it in that way, is the exhaust gas outlet temperature of cylinder 1. And even for such a parameter, we can see a better picture for analysis than for the pure RPM values. So to sum up, in this way, context information might be very beneficial for your evaluations, especially for identifying correlations. And what we did here graphically is somehow find statistical dependencies between the different parameters. And it's really important to find the right parameters on which you're working with, especially if we want to do simulation measurement comparisons. And in case of monitoring systems, as we have heard today, more precise information of the normal operation range might also improve separation between normal and non-normal operation ranges, which also improves the local monitoring system. But at this point, we have additional challenges. So imagine you have gigabytes of data, and you have to find the root cause for any defect in the system. Small parts, maybe just seconds or milliseconds of events, and you have a time series of 1 year, 2 years, and you have to find out the corresponding root cause. This is one topic. So long time range, but short time events. On the other side, you have huge data sets with a lot of variation data, different load conditions, and you should find small trends, for instance, for the predictive maintenance reasons for detecting some kind of wear or something like this. This is also something unimaginably hard to do. And one approach that I've tried to implement in this direction, I want to show, is called the anomaly detection. And to understand what the anomaly detection or how I use it, I want to somehow step out of the TVA context, and I'm presumably now interested in the behavior of fish. And if you're interested in behavior of fish and you want to find out about the psychology of fish, you want to find the one fish or the group of fish which is different to each other. You can go one by one, but it's not very sophisticated. It's only a part of the fish. So it would be very nice to have something or someone telling you, oh, look at this one. This is the one who's swimming in the other direction than all the others. And this is the key principle about anomaly detection. Find some algorithms which mark in the data those positions where you have to look at. And this is done by the anomaly detection, where the idea is to use data, train a model that tries to predict, based on measurement results, the next measurement results, and compute the error. High error levels mean, small error levels mean the training data set corresponds to what we are seeing, so there's possibly no difference between the operation condition in the training data set and in the data set and in the real outcome. Large errors, however, are unexpected. So the training set does not recognize it, and therefore it corresponds to unexpected or abnormal behaviors. And this is the red fish in your data. Come to a real life problem. So we have a system installed on the two-stroke main engine on the container vessel, and we did such a training with 2 weeks of data. It's not much, but it was 2 weeks of data just after installation of it. And after several weeks, we saw 2 significant peaks in the data. So they're really outliers. They are constantly higher than the levels that we're used to see. And we ask ourselves, what happened? What is this unclassified event? And then we also went back to context information and used the GPS data of the vessel. And what we're seeing is, at this time where the 2 peaks were appearing, the Suez Canal passage took place. Of course, it's a container vessel, and the Suez Canal passage, as long as it is possible, is nothing unusual. However, this should really show how to work with the anomaly detection, because in any kind of data, this will be the same way for unexpected events. And since the training data did not contain a Suez Canal passage, it was detected as abnormal behavior. Okay, this was something which was encountered rather soon. However, the initial training of the anomaly detection turned out to be not sufficient. For one part, we did not contain all the information about the standard profile of the vessel, such as the Suez Canal passage. And on the other side, small deviations in the performance, such as ship hull fouling, or something like else, also have tiny influence on the torsional vibrations, which leads to higher and higher levels in the anomaly detection. And with the higher and higher level, the contrast between anomalies and and standard conditions will become less. And it's really hard to define then what is an anomaly. So what to do? Train another model, where you choose a data set that is larger or it's more characteristic for the vessel. And with this, you can reduce the average error level significantly, or in this factor, to say some numbers, 10. Okay, we have now a second model. The story repeats, and we also get rid of the anomaly trending part. So we can train another model. And if you go further and go further and go further, we can see that we have to do an automatic retraining of the artificial intelligence model in order to always have the precise anomaly detection. But what you do on the second stage, you have your statistical model of the quantity of interest anytime you train your data. So tiny effects that would affect the statistics of the quantity of interest would be easily seeable by just comparing the different models. And this is something where you can, out of a large data set, find out small changes over the time. With this, I'm at the end of my talk. I want to summarize that we have to talk about motivation and challenges for using big data in our daily torsional vibration analysis. And I showed you 2 case studies how to integrate big data. The data is half a year old, and it's already rather outdated because we are also facing rapidly changing requirements and technical solutions. So you can always expand your portfolio of the things that you can provide. And this is what we understand as data-driven development. Look in data how we can proceed in this way. And one topic I want to investigate next is torsional vibrations in terms of safety is a rather interesting topic. However, it's such a diverse topic. Maybe one can find a way how to use the torsional vibration analysis data, move it into some other context such as operational data, and find out something about fuel efficiency. Maybe there are correlations, that we can use in future. And this, I think, is a rather good outlook, and it's the end of my story, and maybe in 3 years, or that by the next symposium, we will see what the whole story continued. So thank you very much for your attention.